Okay, I'm testing the BiTT transformer with black sand cores. Not black sand cores, but black sand shunt bars. Top and bottom. It has a 13 UF high voltage AC cap in series from the grid, the red plug, to the primary. The two secondaries are in series. They go into an 82.7 ohm resistor. We have 71 volts across the resistor. The one AC cycle is 23.5 spaces horizontal. There's 5 spaces inside a square division. And at 360 degrees divided by 23.5 is 15.3 degrees per little space. And I have 5.5 degrees between the phase shift of the volts and the amps. The amps is the taller one. And if that is all true, 360 divided by is 15.3, and there's 5.5, it's 84 degrees. Let's say it's 83 degrees. That's what I got before. 0.12 power factors for 83 degree power phase shift. There's 35 spaces vertical for measuring the amperage peak to peak. And it's 0.01 per space. Since it's 0.05 square division, there's 5 in every square division. So there's the math. 35 times 0.01 is point da da da, then times divided by 2 is 0.17 times. It's 0.175 times 0.707 is equal to 0.123 divided by 0.1, because that's the current shunt, is a 0.1 resistor, and we have 1.23 amps circulating, which is about right. And if I used a ammeter to check the amps, it's going to say just about the same thing. So that means the VA is 1.23 amps times 120 is 147.6 volt amps circulating in this thing, times the power factor of only 0.12, and that. So we have a power factor of 0.12, and we have volt amps 147.6, so you times those together and you get 17.7 watts input. And we have 71 times 71 volts, 70.9 now, but 71. 71 times 71 is divided by the resistance of 82.7 comes to 60.9 watts out, because the output is the resistive load and how many volts across it. Very simple on the output, no capacitors. So let's say it's 61. 61 watts output, 17.7 watts input. It's about times 3. That's not bad. So, but, you know, if we do not have this resistor in series, take a look at the scope in series. Oops. Big amps flow, big phase shift. And instead we bypass the cap, so there's no cap in series. Now look at the amps. Not much amps going in. Well, a lot of amps still going in. This comes to about 0.8 amps. Notice the phase shift is about 4.5 phase shift has gone down. And what especially has gone down since I'd say it's about 4.5 degree phase shift. The 360 degree cycle will remain the same. Didn't mess with that. And so without the cap in series, we only have 46.4 volts across the resistor. So using Ohm's law, you square the voltage, 46.4 times 46.4, 46.3 now, and you divide by the resistive load, and let's see what that is. Okay, this is our output now, 25.9 watts, say 26. It used to be 61 when you hook up the capacitor in series, but now it's only 26 watts out. And also, if you figure the phase shift and the cosine power factor, you know, it comes to 0.38. Where is that? I have the it's about 0.38, maybe 0.35. This is figuring 24 spaces to a 360 degree cycle, and it comes to 15 degrees. But anyways, it's about 67.5 degrees, power factor of 38. And now the peak to peak on the amps is only, say, 23 or so. That's what I have written down. And so, blah, blah, blah. It comes to about 0.18, 810 milliamps, amps flowing now, as opposed to what it just was. And which was 1.12. So the amps has gone down maybe a third flowing, but the power factor is like 3 times more. So, and then what's really not so well is before I had 46.7, now I have 46.3. But before, when I do not have the cap in series, it's not over unity. It's about, so this is what I got before, about 20 minutes ago. 37 watts in, 26 watts out. The cap really affects the output. And I think it's because it's got a lot more amps flowing, and it really kind of activates the shunt bars so they do what they're supposed to do. And one thing they do is really make a good phase shift going on. A wide phase shift. And so there's a lot more amps flowing. It doesn't matter when you have a 0.12 power factor. Look at this, this is what I got before. 156 VA, because it's 120 volts times 1.3 amps. This is earlier. I have 1.23 amps now, but you know, it's pretty close. So I had 156 volt amps, but a power factor of 0.12. See, that brings the watts input down to like 18.7. And what I just got now is 17.7 watts. So it's just over 3 times more output than input when you have a 13 UF series cap from the grid to the primary to kind of boost the amp circulating, which boosts the output very significant, and it creates a bigger phase shift so that you have very low power factor. So when you start approaching 90 degrees, you start getting these power factors like 0.1 or even 0.05, stuff like that. So it doesn't matter how big your VA is, if it makes your power factor. If you cut this down to 0.06, you know, and you have 200 here, so you just get that power factor is so important to get that watts down on the input. So there is that. And so it's working good now. You know what I think I lost my power factor, my phase shift, when I did the cap in series, and I think I had the scope volts on the wrong side of the capacitor, not on the input to the capacitor, but on the other side. I think that's what happened. And regardless, I'm glad I changed to black sand cores because they seem to work better, and they're certainly a lot easier to make. Now I'm making another one coming up, and this has 8 parallel wires of 61 feet each, and it's 28 gauge wire. And this one, I showed the last video, I showed how I'm going to have the black sand, and I had to wind the coils and stuff, so I took all the felt structure off. But what's going to happen is I'm going to have black sand on both sides of this section of the crossbar at the end, the cube section, maybe you could call it, above the secondary. So I'm going to have black sand here too in the end, maybe that wide, maybe 3/8 of an inch coming out, and I'm going to have it on this side and this side, and of course I'm going to have it going up and over. So I'm going to be catching the back EMF flux with this black sand chamber on this side, this side, this side, and this side. So it's like 4 times, maybe 3 times more area is going to be getting absorbed, I guess you'd call it, or redirected by the shunt bar made of black sand. So I have a feeling this one's going to be really a good one. And also I think I can get over 90 degrees if I drop this resistor down to about 50 ohms or 40 ohms. But right now I like it just approaching 90 degrees. Keeps everything above the table. So, okay, so that's my latest video. Things are working pretty good. Black sand cores or shunt bars are going to be working good, I'm sure. I have a lot of black sand. I have this one over here too, which I'm probably going to take these things off and do shunt bars, black sand on these, but I don't know about that for now. So, also working, I'm trying to make an inverter that will reflect, I guess you'd call it, the reactive power. And idea here is I'll be using bidirectional MOSFETs that can switch AC because their grounds, their source leads, and their gates are connected, and the switching goes between drain A and drain B. And that's what I have now. I have actually 2 MOSFETs on there connected like that. Source leads connect, gates connect, drain A comes in, drain B goes out, or the other way around, so it can switch AC. So if I have these sort of switches, it should allow the back currents to go back. The back EMF back currents should have a route backwards, not blocked by the MOSFET. And when it goes backwards, could maybe fill a cap or something. So I'm working on this inverter. So anyways, there's all that. Thanks for watching.